Hi. In this video, we're going to talk about the calculus of parametric curves, or calculus with parametric curves. So in the previous video, we defined x as a function of t and y as a separate function of t. And we said this would be useful for describing the motion of a lot of objects. And you should recall from Calculus 1 or from Calculus AB that calculus itself is very useful for describing motion. Whether you're talking about position or velocity or acceleration or even other topics we covered, this should be a necessary idea. Whenever you're thinking about motion, you should kind of think about, oh, well, calculus might help us talk about it. The simple version here, one kind of calculus we can do, the easy kind, would be to say, like, oh, well, I could just differentiate x with respect to t. I get like f prime. I could differentiate y with respect to t and get g prime. Now, the common issue is that a lot of students think, oh, derivatives are slope. So I just got some slopes, right? Now I want to be clear here. You got the slope of the f function or the slope of the g function. What you don't have with either of these is the slope of our parametric curve. So that's my first really important warning, is that neither, and this is always true, dx dt or dy dt, maybe it should be nor there, I don't know, tell me, or anybody, the slope of my parametric curve. It just doesn't, okay? It can tell you other things. They will tell you something like, oh, how is x changing over time? How is y changing over time? What's the velocity in the x direction? What's the velocity in the y direction? And if you actually look back at Calculus AB or Calculus 1, you would see that that's always what the question was saying. It was never going to say, what's the velocity in general? It was always the velocity in one specific direction of motion. And just to be clear here, we want to talk about the slope of the parametric graph, the parametric equation. And just to be clear, I'm talking about if you grouped it as x comma y equals f of t, y of t. Or g of t, sorry, g of t. Now we do want to talk about the slope. The slope of the curve, of, again, the parametric curve, the thing we're trying to talk about, the motion of the spider or the fly or the ant, sorry, the slope of the parametric, I don't know why I broke it into two words, I meant to probably do that. Parametric curve will still be, is still dy over dx, the classic change in y over the change in x. But how we're going to get that is a little more complicated. You might notice that it should stand for the derivative of y over the derivative of x. And in that case, that's what we're going to do. We're going to have dy dt divided by dx dt. Notice it's not the quotient rule. It's a little like L'Hopital's, but I hesitate to say that. L'Hopital's is going to come into play here, but in general, this is what we're talking about when we talk about slope. So, for instance, let's do an example. If I had x equals secant of t, y equals the tangent of t, let's say someone asked me to find the equation of the tangent line at t equals pi over 4. And you might remember that could tell us quite a lot. So whenever you see this direction, it's still true. Whenever I see find the equation of a tangent line, I need a point and I need a slope. Right? That's the kind of equation we're going to use. So for the point here, this is just like in the last video, we're going to be using x comma y at t equals pi over 4. So this is the easy part. We're just going to have x equals secant pi over 4, which is root 2, and y equals tan of pi over 4, which is 1. So the point we're using is going to be root 2 comma 1. For the slope, again, you're not thinking about dx dt and dy dt. Not immediately. You should make sure you're saying, oh, it's dy dx, which is that formula. Dy dt divided by dx dt. Now, I still need to find dx dt, which is, again, the derivative of tan. Secant is secant tan, like that. And so, and dy dt, I guess we'll do it that way, is secant squared. So the equation for, I guess I'll do it this way, the equation for dy dx is secant squared, the y over the x. Which of course can simplify to secant t divided by tan t. And you could simplify that, but I don't really need to. And that would be the equation of this parametric curve. And notice I'm not graphing this. I don't really care what it looks like. We could find out using a table, not so much using any identities or something. But so dy dx, when we evaluate at t equals pi over 4, notice I'm evaluating at a t coordinate. I don't need this information. I don't need the rectangular point x comma y. I only need t because that's what's going into these functions. And again, we talked about this already. Secant t is root 2. Tan t is 1. So we have a slope of root 2. Putting it all together, y minus 1 equals root 2 times x minus root 2. Okay, and that would be my tangent line equation. That's it. So the complication can come in because it's defined as a quotient. We need to worry about horizontal and vertical tangent lines. Now, as always, we're interested in those. That's very interesting stuff going on. A vertical tangent line meant something about the direction of travel, the steepness of the curve. A horizontal tangent line meant something specific as well. So what we want to do here is, since dy dx equals, again, I'm going to write this a million times. Hopefully you start to remember it by the end of this lesson. You will need to remember this eventually. Okay? Now a horizontal tangent line meant dy dx, again, not dy dt or dx dt, equals 0. How do I have this fraction equal to 0? So if I have a fraction equal 0, like dy dt over dx dt equals 0, that will be enough to show that dy dt equals 0 and dx dt is not 0. If they are both zeros, there's going to be an issue. I'll talk about that in a second. My vertical tangent line, we'd have dy dx undefined, right? The slope of a vertical line is undefined. And if I had a fraction that was undefined, it probably means the denominator equals 0. But again, and dy dt is not 0. Sorry, I'll clean that up. Dy dt is not 0. All right, so I want you to be really clear about these conditions. A vertical tangent line means dx dt is 0, dy dt is not. Or horizontal tangent line, we're going to have dy dt is 0, and dx dt is not. In case you're curious, if they're both 0, this won't happen. If they're both 0, use like L'Hopital's. Everything's a limit. Derivatives are a limit. Integrals are limits too. Not that that's here yet. That's what we would use. Use L'Hopital's to decide which one's going to 0 faster, more or less. Okay? It's not determinant. It's indeterminate is the highlight, which you should remember from the situations with L'Hopital's. Okay, so example of that. We have x equals t squared, y equals t cubed minus 3t. I want you to find the intercepts, both x and y, the horizontal tangents, and the vertical tangents. Then graph. So if you find all this stuff, it's because it will end up being easier to graph after you do all that. Again, if you wanted to graph this, you could try our other methods from the last video. You could try solving for t and then substituting. I hope you can see how that's not going to go so well here. So instead, we're just going to do this process. We're going to find the intercepts, the tangent lines, and then graph the special tangent lines. So intercepts. I'm only doing this because I need a graph. Like it's still the same old story. Y-intercepts, we want x equals 0, and then find y. Now, usually I would have said solve for y. I almost wrote that here. But in case you're missing it, this is going to be a little more complicated of a process for parametrics. So if x equals 0 and x equals t squared, we're talking about t squared equals 0, which means t equals 0. When I plug that into y, and I get 0 cubed minus 3 times 0, which is just 0. So our y-intercept is 0, 0. Easy peasy. X-intercept. We start with the idea that, well, y would be 0 at an x-intercept. So 0 would be t cubed minus 3t. Start factoring it. And hopefully you would get 0 and then root 3 and negative root 3. Now for t equals 0, we just did that. X equals 0. That's our y-intercept, right? That y-intercept is always an x-intercept. For t equals root 3, x would be 3. And the same thing's true for t equals, negative root 3. X would be 3. Okay? So we're talking about the points. I'm going to shrink this in a minute because I'm clearly going to run out of room. 3, 0, 3, 0. It's the same point, right? This would mean the same point because they have the same y's. Let me erase this because it's going to look silly. And obviously 0, 0, though, still is an x-intercept. Usually I would list them both. It's an x and a y-intercept. Hopefully that all makes sense. Make sure it does before you go into the next one. It's not just that the x's are the same at the same point. I will say this really quickly. It's that the y's are the same too. It's the x's and the y's that make it the same point. So I'm going to graph it down here. I'm just going to keep track of what this means for us so far. I guess I meant to say it's the same point at different times. Okay, that's going to mean something. But so far, the only data I have is 1, 2, 3, 0, and 0, 0. All right, horizontal tangent. So anytime you're talking about slope, you are going to have to find the derivatives with respect to time of both of them individually. So let's talk about dx dt is 2t. dy dt equals 3t squared minus 3. And for horizontal tangent, we want dy dt equals 0. dx dt, dx dt not. So 0 equals 3t squared minus 3. You should get t equals plus or minus 1. Will either of these values make x equal to 0? No, sorry. Will either of these values make dx dt equal to 0? No. So at t equals positive 1, our coordinate would be 1 comma negative 2. At t equals negative 1, still going to get 1, but now we're going to get positive 2. So 1, 2, I'm graphing in the lower left-hand corner. And what we know at those points is a horizontal tangent lines happening. We know that's going to be tangent to the graph. And that will end up telling us something kind of important when we go to draw it. I am going to shrink this horizontal tangent line mention work. Sorry, not mention. All right. Okay. Last but not least, dx dt equals 0 to find the vertical ones. dy dt, sorry, dy, all right, nice, dt is not 0. So we'd have 2t equals 0, t equals 0. We just checked that does not make dy dt equals 0. And in fact, we know what it did already. We found this point. So there's a vertical tangent line at the origin. I just drew a blue dashed line there to represent what's going on. And what's going on here, in terms of finding out where it starts, you'd have to maybe try some other points analysis. I'm just going to try to sketch the curve really quick. What we have is it's going to kind of, at t equals negative 3, we're here. And then we're slowly going to get more and more positive. We know that we're going to go toward other important values. Like, right, that was t equals negative root 3. This is t equals negative 1. So it's progressing this way. Notice I'm drawing a horizontal tangent there, a vertical tangent there. Actually, I don't like how it looks, so I'm going to restart. Perfectly horizontal there, or at least as close as you can draw. A vertical there, back to a horizontal there. And then we know it actually comes back to here at positive root 3. So I'm going to head in like that. And in fact, what happens is it goes, oh no, it goes through and through. And that's the orientation. And to be sure what the end behavior looks like, you would use other techniques that we've discussed, but you don't have to worry about that too much. Just trying to show you how the graph works. And so it's like that bow tie shape. That's why horizontal and vertical tangents are useful. Okay, moving on. The second derivative is going to be even more complicated. And we're not going to motivate this with any formula. It's not going to look like it did before. It's going to be kind of ugly. So again, this kind of thing is useful because it still tells us concavity. It tells me the concavity of the graph, of the parametric curve. Not the derivatives of y or the derivative of x by themselves, right? Not dt. This is not a dt. So this is going to be a really complicated formula, or sorry, it's not that bad of a formula, it's just hard to remember. So what this says is we're going to take the derivative of dy dx. I'm going to point out that that's an x, but this is a t on the outside. We're going to take the derivative with respect to t of dy dx, and we're going to divide by dx dt again. And it kind of makes sense what's going on here, but it really doesn't have to. If you want to follow a proof of this, we could talk about it in office hours, but this is the formula we'll use. Okay, I'm just not going to get into any kind of proof of this. So if we had x equals the square root of t, y equals 1/4 t squared minus 1, they could ask us to find the slope and the concavity at 2, 3. Okay, so start with this. Let's try to find the slope. Okay. When we're trying to find the slope, we're talking about, again, y dx. And we're talking about dy dx. We're not talking about dy dt. It's dy dt over dx dt. Now, luckily for us, this is kind of a straightforward derivative to take. We have 1/2 t on the top. And on the bottom, I'd have 1/2 t to the negative 1/2. So the 1/2s will cancel. And if you subtract the powers, you should get t to the 3/2. Please be very careful. You do want to have this simplified because we are going to take its derivative again. Why? Because to find the concavity, we're talking about the second derivative, which says take the derivative of the slope, divide by the derivative of x by itself. So the derivative of the slope is 3/2 t to the 1/2. Make sure you understand where I'm getting that from. It's coming from, I'll highlight it in yellow. That's dy dx, okay? That's what I plugged in there. That's what I took the derivative of with respect to time. And the dx dt you already found, if you're paying attention, it was 1/2 t to the negative 1/2. And I'll highlight the ones that match here. This is dx dt, okay? And when you simplify this, you should get 3t, which is like a surprisingly simple formula based on all the craziness that was happening. But again, if you just make sure you do your calculus calmly, everything should go fine here. Now, the next trick I'm trying to show you about here is it said at 2, 3, we need a t value. Like if you look at our equations, they both have t's in it. So if you need the t value given a point, solve and check, I guess I'll say. I'll be clear about that in a second. So we know x equals 2. So I know 2 has to be the square root of t, and t would have to be 4. Now, you don't want to just use that. You might have situations, depending on the functions used, where you'd have 2 possible values for t, because again, it might hit the same point multiple times or the same x coordinate. So I'm just going to check that in the y. If I have y equals 1/4 4 squared minus 1, I would get 4 minus 1 equals 3. check. That's what I mean by check. In case you're not seeing it, the y coordinate ended up matching. That's what we're using. So, wrapping it up, dy dx at t equals 4, 4 to the 3 halves, which is 8. And the second derivative is simpler. I'll have to squeeze it in, but it is at least simpler. It's 3 times 4, which is 12. Okay, so what do we know? We know the graph is increasing because we have a positive y dy dx. Like the x coordinate, as the x coordinate is increasing there, the y coordinate is increasing. It's a positive slope and is concave up, right? That's what the positive second derivative meant. So make sure you practice this on your homework. We're going to do one more concept, which is really important for motion. We have arc length, which again, you should have covered in a Calc 1 class or a Calculus AB class, but briefly. Maybe it's in BC, I'm not sure. But in Calc 1, or at least what I think is Calc 1, you have the length of a curve is given by this following integral. You go from A to B, and those are x's usually, and you have the square root of 1 plus f prime of x squared dx. Okay, that might look familiar, it might not. I'm just reminding you of it in case, so we can start to see how a lot of these formulas you have for length look similar. So this is the length of a curve. It can also be describing the distance. I'll say that again in a minute. So for parametrics, the idea is, and this is where the other formula came from too, it's just simplified. My hint. So parametrics, we have a curve like this, and I wanted to find the length of it. Why are we using an integral? We want to understand what a small length is doing and then add them up. So here's a small little length there. If I looked at that small length, I'm going to blow this picture up. So in magnification, it looks like you have a curve like that and a really tiny change along the curve would be pretty much straight, as straight as you want it to be. And you could break it into components, like a small change in y and a small change in x. And so therefore this would be the square root, using Pythagorean theorem, dx squared plus dy squared. Whoops. Let's just call it dy squared. And that's exactly what we're going to do. So that small change in length, s is sometimes used for length, would be that Pythagorean formula. So what we have is that the arc length of a parametric curve, which is also the distance traveled, is an integral from a to b, the square root, and what's dx dt? Well, sorry, what's dx? Spoiler. Dx is dx dt. Dy is going to end up being dy dt squared with respect to time. That's it. That's the formula. It should look a lot like the one before. It really is the same. I guess that top one is useful. The one from Calc 1, we're saying, is useful because it would have perhaps be easier to use in some cases, but a lot of times we like this just fine. So let's do an example. For this example, we're just going to find the formula. A lot of times these problems don't work out nicely. So we're just going to try to find a formula for the length, the length of x equals 3t minus t squared, y equals 4t to the 3 halves on the interval from 1 to 2. So for this kind of thing, you want to find dx dt, which is just 3 minus 2t, dy dt, which is just 6t to the 1/2, or the square root of t. And then my arc length formula, and this is all I would really want you to do, is the integral from 1 to 2. And in case you're getting super lost, those numbers are just coming from my interval. They're pretty much always going to be given to you, unless it's kind of easy to find. The derivative of x, quantity squared, plus the derivative of y, quantity squared. And that's just something you could punch into the calculator. You can't really do it by hand. I may or may not have tried to and messed up. So anyway, thank you for watching this. Please try out the homework. Good luck. Have fun. Bye for now.